Well, hello everyone, and welcome to the presentation concerning the size effect on the apparent tensile strength of brittle materials with spherical cavities. My name is Arturo Chao Correas, and I am a PhD student at the Department of Structural Building and Geotechnical Engineering here at Politecnico di Torino. This project has been developed within the Horizon 2020 Marie Curie-funded NeoFrac Innovative Training Network. I hope that you all will enjoy this presentation, and without any further ado, let's go straight to the topic that concerns us today. The case we'll be addressing in this presentation is that of an infinite or at least sufficiently large domain filled with a homogeneous, isotropic, and linear elastic material that contains a single spherical pore. This pore is not pressurized and the domain is under uniaxial tensile load. Therefore, we can treat this problem as axisymmetric. In this condition, the stress field in the Boyce equator, which is the highest stress area, is given as per the equation on the left side of your screens. Therefore, the resultant maximum stress concentration would be of the order of 2 and weakly dependent of just the Poisson's ratio. Since the stress does not diverge, it could be natural to apply the maximum stress criterion to predict the failure in these conditions, according to which just one pore of any size would cause a circa 50% weakening of the specimen in comparison with the pristine conditions it is without any pore. However, this is in direct opposition with the experimental results by Bertolotti and Fulrath, shown on the right side of the screen. This experiment showed that, in fact, even for very low porosities, there might be a noticeable weakening, but with a magnitude dependent on the pore size. And this is what we call size effect. As a result, we can firmly state that the stress criterion is not suitable for use in this case. It is also known that the size effect is a particularity of linear elastic fracture mechanics solutions, which in essence are energetic balances versus the material fracture toughness. However, in the considered case, this formulation is not straightforwardly applicable due to the lack of a pre-existing crack, which, according to the energetic balance of linear elastic fracture mechanics, would lead to infinite strength predictions. Thereafter, other applicable theories have to and will be presented. Now, the simplest theory for predicting this size effect would be to use the equivalent linear elastic fracture mechanics, which is just an extension of the conventional formulation that allows its use in uncracked bodies. This one is based on two basic concepts. First, crack sensibility, and second, inherent cracks. It is known that even for cracked bodies, like the Griffith crack on the right side of the screen, and making use of conventional linear elastic fracture mechanics, there is still a range in which the failure is strength-driven, and so the solution is independent of the presence of the crack, should this one be shorter than a certain length, called A0, and whose definition in terms of the fracture toughness and material strength is seen on the screen. Therefore, we can consider that any domain always possesses an inherent crack of length A0 in every surface, and that failure is then governed by the crack that yields the lowest failure load according to the linear elastic fracture mechanics criterion. On the paper by Taylor et al. From 2005, they reached this very same conclusion herein presented, although they used a different reasoning. And in that work, this formulation was referred to as finite fracture mechanics. Then the stress counterpart of equivalent linear elastic fracture mechanics is the theory of critical distances, in which you calculate an equivalent stress called sigma star over a certain length ahead of the stress concentration. The equivalent stress definition depends on the variant used, and it can either be the point-wise stress at a certain distance, the so-called point method, the average over a line method, or over an area method. Only the two first methods are considered here. Moreover, it can be seen that the material fracture toughness is inherently considered in the length definition through the Irving's characteristic length, LCH. Then failure is predicted to happen when this equivalent stress reaches the material strength, sigma c, for the case of no plasticity. This set of formulation has been used in many scenarios despite its simplicity, although it has some limitations for non-monotonically decreasing stress field or tensile compressive scenarios. However, there are some other more developed theories applicable. One of these is the finite fracture mechanics, a relatively new framework from 2002 that considers a coupled stress energy criterion for fracture prediction and has already been successfully applied to many stress concentrations, such as circular holes, notches, or beam ligaments, proving its robustness. It considers that an spontaneous crack propagation occurs over a certain finite length, delta big sub c, at a failure load, sigma f. This solution is given by a minimization condition problem as shown. Although for positive geometries with monotonically decreasing stress fields, this is simplified to a nonlinear system of two equations. The main advantage of this theory is the use of an inherently defined length, which allows its use for much more complex scenarios, given that this length is able to modify itself. Eventually, the last framework he considered is that of the well-known cohesive crack model. This work will only address the variant proposed by Dugdale, i.e. the cohesive stress being constant with the crack opening. This model works by dividing the domain into two regions. The elastic one, whose constitutive equation is in terms of the stress versus strain, and the cohesive one, whose behavior is defined as a stress versus crack opening relation. This region is also referred to as fictitious crack. The change from elastic to cohesive is irreversible, since it considers that some damage appears in the material, and happens when a stress threshold is reached. Eventually, crack propagation occurs at the mouth of the fictitious crack when the stored cohesive energy per unit area reaches the fracture toughness Gc at this point. As a result, the solution is given by the following system of two nonlinear equations with two unknowns: the failure load sigma f and the fictitious crack length a sub p. Once presented all the formulations that we will be using, let's see how each of these are particularized for the spherical void case. First, equivalent linear elastic fracture mechanics and theory of critical distances are the two most simplest cases, each of which only requires one function input, which is either the stress intensity factor or the stress field, respectively. Then the solution is given by one single equation with one unknown, the weakening ratio. For the case of equivalent linear elastic fracture mechanics, the coefficient 1.122 refers to the stress intensity factor geometric function of the edge crack, which could be the case to analyze for an unvoided specimen. The minimum operator allows to compactly define the transition from stress to toughness-driven failure. For the theory of critical distances, both point method and line method are here considered. On the other hand, finite fracture mechanics and cohesive crack model present an increased complexity, requiring two or even three input functions. The resolution of both is defined by a system of two nonlinear equations with two unknowns for this case. For the finite fracture mechanics, both the original and average stress formulation are here presented. Notice that only the stress criterion changes between these. Then, for the cohesive crack model, three input functions are needed. The last stress intensity factor function can also be substituted by the crack mouth opening displacement if this expression is known. The minimum operator, in this latter cohesive crack model, simplifies the subsequent numerical resolution of the system by avoiding the divergence in AP noticed by Cornetti and Sapora in 2019 for vanishing size of the defects, although in that later work they were dealing with penny-shaped cracks. Therefore, it is seen that the characterization of the annular crack in terms of the stress intensity factor is fundamental for most of the formulation presented. These expressions can be analytically approximated by considering the limit cases of cracks either much larger than or much smaller than the void, which would resemble to a penny crack or an edge crack respectively. Notice that each of these would be loaded by the equator stress field due to the spherical void. These fundamental solutions might be then obtained through the weight function method, as it was done in the work by Theo Fett in 1994. Then these solutions are interpolated with a proper function, beta, that complies with the streaming limit cases. In this case, it has to comply that beta, when A is much larger than R, has to tend to 0, and beta, when A is much smaller than R, has to tend to 1. As the crack mouth opening displacement is also required for the cohesive crack model, the Paris equation, particularized for the axisymmetric problem, allows to relate this magnitude to the stress intensity factors, allowing to define the cohesive crack model system of equations entirely dependent on the stress intensity factors for annular crack of surrounding an spherical void under different loading cases. This relation is also rather interesting for the comparison of the analytically and the semi-analytical stress intensity factor functions with finite element simulations. Then, through this semi-analytical procedure that we have just presented, it is seen that upon a correct choice of the beta function, very good agreement might be obtained in comparison with finite element results. Now, we can show the predictions respective to each formulation, out of which we can conclude that the theory of critical distances delivers the most conservative fracture predictions, whereas cohesive crack model generally yields the most optimistic fracture predictions. Both versions of finite fracture mechanics are relatively close, being always the finite fracture mechanics average stress more conservative than the original finite fracture mechanics. The former also provides a smooth version of the prediction by equivalent linear elastic fracture mechanics. Generally, all the predictions agree to predict the transition between the unvoided and large void solutions in the range from 0.1 to 10 LCH in the Irving length. This has large implications for industrial applications, since once known this Irving's length LCH, the minimum resolution required for the structural inspection techniques looking for these pores could need to be at least 10 times smaller. Any undetected pore smaller than this threshold is potentially not dangerous. Eventually, the experimental results of Bertolotti and Fulrath are a useful tool to check the validity of the method here presented and developed. However, the brittleness of the material used, the borosilicate glass, makes it really important to control the experimental procedures. For this experimental campaign, Bertolotti and Fulrath introduced control porosity in borosilicate glass by adding nickel spheres during sintering. After cool downs, the particles, which were surface treated for not adhering to the surrounding material, shrank more than the ceramics, leaving, from a practical point of view, spherical voids. Then specimens were 4-point bending tested, and the maximum force recorded was considered for strength calculations. Out of these experimental results, the two least porous cases, 2% and 5% porosity, are compared with the predictions with rather good agreement between them. It is worth highlighting that no fitting parameters were used for this comparison, just the material structural properties LCH and sigma C, as well as the void radius R. It is especially remarkable the good agreement of finite fracture mechanics, average stress, and the mean experimental results respective to the lowest porosity case. Eventually, we can draw some conclusions out of this analysis. In the first place, the weakening of a single spherical void in a brittle material is dependent of the pore size, and this behavior is toughness related. To characterize the stress intensity factor of an annular crack surrounding the spherical void, accurate semi-analytical expressions might be derived. 6 different frameworks have been developed with good agreement between them. All of them place the transition from unvoided to large void solutions between pore radii from 0.1 to 10 times the Irving's length. The latter solution leads to a strength reduction of up to 50%, weakly dependent on the Poisson's ratio. In particular, finite fracture mechanics average stress presents rather good agreement in comparison with the lowest porosity case of the experimental results. To close this presentation, I am glad to acknowledge the funding received from the European Union's Horizon 2020 Research and Innovation Programme through the NewFRAC Consortium. Thank you all for your attention, and I will be happy to answer any doubt that you might have during the conference.